All right, Emicle, I am sorry that you are unable to be here tonight, but yeah, I wanted to share a little bit before we start on just going over some revision of electrochemical cells. I remember you mentioned in the previous session that this is probably one of the more difficult ones for you to work with, and that it has been some time. So I'd love to just do a very brief overview now here before we continue with the question paper that we were on, and that was last time. That was paper 2, November 2021. But let's just have a look first at electrochemical cells. Electrochemical cells there are two different types of cells. There are galvanic cells, where we have chemical energy going to electrical energy. And that is a very typical car battery. Car battery is a type of galvanic cell. But then you also get electrolytic cells. And electrolytic cells are not the type of cells that we use to generate electricity, but these are rather the cells that use electrical energy to go to something chemical, to create a chemical reaction. And the reactions that they use, both of these use, are redox reactions. And just a small reminder of what redox reactions are. That is when we have a combination of some elements losing electrons and some elements gaining electrons. And we saw from the previous session that when an element loses electrons, we call it oxidation, because oxidation is loss. And also likewise, we had another way of remembering what is reduction. When we gain electrons, reduction is gain. When an element undergoes reduction, then it is gaining electrons. Another way of, so oil rig is a nice way to remember it. Another way of memorizing it is also Leo goes Gur, and so loss of electrons is oxidation, and Leo goes Gur because gain of electrons is reduction. But either way, it's up to you. I prefer oil rig, and so let's stick with oil rig. And we also now had to have a look at these different types of reactions. We had to look at combining them in the different structures. Now, I mentioned previous time that galvanic cells have two beakers, two separate beakers, like this here on the left-hand side, where we have on the one side of the beaker, we have oxidation going to take place. And on that side, oxidation is taking place, so they lose electrons, and therefore the electrons move all the way up. They are able to move across this conducting wire. On the other side, we have reduction taking place because those same electrons are going to be moving up to this side. And in this side, we have elements gaining those electrons that are coming in. Those electrons coming in are gained, and some reaction takes place. So that's what a galvanic cell looks like. We also have this salt bridge in the middle. This salt bridge has multiple purposes. Remember, if this is an electric circuit must be closed. So it closes the electric circuit. It also allows us space for electrolytes inside the salt bridge to balance out. And so if we have on the right-hand side here, we have reduction taking place. We will have this electrolyte, this solution here, just filling up with so many negatively charged things. So we will have that this salt bridge allows cations to flow into this solution, into this electrolyte, and so that balances out the negative ions that are left in there. And the same with the anions. The anions from the salt bridge move to the left, and they balance out the positive charges, though, the positive ions that are left behind when all the electrons are popping off. When all the electrons are being lost, it leaves us with positive ions in this electrolyte. But the anions come in and they balance this. And so salt bridge is really there for multiple reasons. But that is going to be for you to study. I'd like to get into just a few understanding things. A few important things here that I want to point out is an electrode where oxidation occurs. That is always going to be called the anode. Okay, this is true for all electrochemical cells. And where the cathode, we have reduction taking place, right? And so let's have a look. We see the exact same. On the electrolytic cells, we don't have two beakers, but we have one beaker. and one anode and one cathode, but still we have the anode is where oxidation occurs, and the cathode is where reduction occurs. And note what's happening here on this electrolytic cell. Instead of something like this, like a light bulb on the galvanic cell that can be lit up, on the electrolytic cell, we actually have a DC power source, like a battery. And it is powering this chemical reaction. And this chemical reaction, we have if the positive side of this battery or this power source is here on the left, then the electrons will be drawn to it. And so that makes the anode, if it's losing electrons, that makes the anode a positive because it's losing electrons. If the electrons are being lost, being pulled away, that leaves a positively charged anode. And so on the anode, we have a positive charge on the electrolytic cell, and the cathode a negative charge here in the electrolytic cell. But on the galvanic cell, it's different because the chemical reaction is the driving force here. It's not being driven by a DC battery. The chemical reaction here is oxidation, and so it's pushing electrons. It's losing electrons. And so it's losing electrons to this anode over here. And so that anode now becomes negatively charged because it's gaining electrons. That's an important thing to just to bear in mind, is that on the galvanic and the electrolytic cells, we have the anode being oxidation, anode and oxidation, cathode and reduction, cathode and reduction. But on the galvanic cell, the anode is negative and the cathode is positive. But on the electrolytic cell, it's the other way. The anode is positive and the cathode is negative. What's important here is in the galvanic cell, the reduction, the substance that is undergoing reduction, it is gaining electrons quite comfortably. It really wants to gain those electrons. And the anode, the substance that is undergoing oxidation, is losing electrons. And it really quite comfortably wants to lose electrons. If the one side wants to lose electrons, and the other side wants to gain electrons, and they both want to do so, then this redox reaction will happen spontaneously. Okay. This is true for all galvanic cells. Galvanic cells have redox reactions that happen spontaneously. But with electrochemical cells that don't want to happen that spontaneously, we actually have to force them to do it. That's why we add the battery. The battery is there to force the redox reaction to take place. And so redox reactions do not occur spontaneously in electrolytic cells. Okay. I really hope this gives you a good foundation as we start off on this next section, because I'd like to continue on the question that we were busy with. We were on this question 8 from 2021, paper 2. Right, so let's continue here. They asked us, they gave us this electrochemical cell under standard conditions with a half cell A and a half cell B. And we found that, okay, this is a chemical energy to electrical energy. This was a galvanic cell. And we did some calculations. We found that the redox, or the reduction taking place, is the silver, and the oxidation taking place is the copper. And the reason we could have known that is because when we had a look at the reduction potentials table, remember, choose one and stick with it. We found that silver and copper, both of these reactions taking place here, the silver is higher up on the reductions potential than the copper was. The silver is more likely to reduce than the copper is. And so therefore the silver underwent reduction in this forward reaction, because reduction is gaining of electrons. But the copper underwent oxidation, because this is a dual. You have two sides of the same coin. Reduction and oxidation can't happen each on their own. They need to happen together. And so if silver underwent reduction, copper underwent oxidation. And we go in this clockwise rotation when we are using this reduction potentials table for galvanic cells. This is really important. Okay, and so now knowing silver went that direction to the right, it gained electrons. Oxidation for copper should have been to the left. And so instead of saying copper 2 plus 2 electrons, we know it's happening the other way around. It's copper going to copper 2 plus and 2 electrons. All right, so we used that and we found the balanced chemical equation for this reaction, this redox reaction, and that's where we stopped. I'd like to now move on to question 8.5, and I'm going to move over to the right-hand side here. We're saying the initial EMF of the cell, that's what is the EMF that the cell is making. And there are three formulas. All three of them are on the formula sheet, and all three are valid. They all three work exactly the same. And I'd like to just have a look here how we use each of them. A reminder that at the cathode we have reduction for galvanic cells, and the anode we have oxidation. It's the same for electrolytic cells, but this is a galvanic cell because it's got two beakers, two half cells. That's a galvanic cell, chemical energy to electrical energy. And so if the reduction takes place at the, here we go, the reduction is taking place at the cathode, and the oxidation is taking place at the anode. Apologies for that, a bit noise. Right, so let's have a look. Now that we know where the reduction is taking place, now that we know where the cathode is and the oxidation in the anode, we can also take note, remember the thing that is undergoing reduction is called the oxidizing agent. Okay, we spoke about that the previous session. If you missed that out, I'll make sure that the video is uploaded for you to also go and revise. Now, how do we use this formula? We say that the E of the cell is equal to the reduction potential of that is taking place at the cathode, and we subtract the half cell voltage at the anode. And this is true for all the other equations, for all the other two equations as well, because at the cathode reduction is taking place, and where reduction is taking place, that thing is called the oxidizing agent. And so all three equations are exactly the same, but you're only allowed to use these three. Any other variation, any other wording will automatically deduct a mark. So please just watch out there. Please, you have to use these correct terms. Okay, you can use one of these three. You don't need to use any one specific, but any other variation will not be allowed. Okay, so let's continue here. We've got what was the reduction potential at the cathode, and remember the cathode was the silver, and so we'll go over to that on the reduction potentials table. The silver's E value there was plus 0,80, and so we will make that, we'll add that in here, plus 0,80, and then we subtract the anode, which was 0,34. 0,34. All right, and when we do this, we do the substitution, we find that this will be 0,46 volts. Now, this is the voltage or the EMF that is induced when we hook up these two half cells. And this happens spontaneously. This occurs. They will automatically generate 0,46 voltage of EMF. So that also tells us that this will be a spontaneous reaction. Yeah. This will also only be the case as long as it's set up under standard conditions. But as the reaction continues, that concentration in both of the half cells will diminish. And so this will not be a permanent 0,46 voltage. With age and with time, it will decrease. Let's have a look. 8.8.6. How will the EMF of the cell be affected if the concentration of the copper ions in half cell A increases? And so what I just mentioned there was, if the concentration goes down, then we will have a lower voltage, a lower EMF. But now what is going to happen with the concentration of the copper ions in the half cell A? What's happening at half cell A? Let's have a look at half cell A. Half cell A is the oxidation, it's the anode. That's when copper is going to copper ions. So if I'm increasing one of the products, that means I am limiting the forward reaction. Now that's bringing in some ideas from a reaction, rate of reaction. But if I'm limiting the forward rate of the reaction, that means I'm limiting the oxidation. That means that if I'm limiting the reaction, if I'm limiting this redox reaction, it means that this cell will not be as efficient. And so if the concentration of copper ions specifically there would increase, how will this affect the EMF? Well, the EMF is dependent on how well this reaction takes place. If the reaction is going to be less efficient, then, oh, sorry, that's Afrikaans, then the EMF will decrease. And the reason for this is that we are limiting the forward reaction by doing that. They are not asking us for a reason, and so we'll stop right there. And nice, let's look at the allocation of marks. One for the formula, one for cathode, one for anode, and one for final answer, and then 1 mark for decreasing. All right. I really hope that this lays a proper foundation for electrochemical cells. I will make sure to upload this for you as well, but we will continue on now, directly jumping into this, what seems to be not a galvanic cell anymore, but an electrolytic cell. And they tell us here, the diagram below shows a simplified electrolytic cell used to electroplate a ring. Now, we haven't spoken about the applications of electrolytic cells, because I specifically mentioned that they have been removed from caps, but I think this would be very good practice for understanding electrolytic cells, because you will still be tested on electrolytic cells. I want to look at one specific one after this. So in here we've got question 9.1, define the term electrolyte. That's a very good one, because we have in each of these beakers, both galvanic and electrolytic cells, an electrolyte. Okay? And an electrolyte is a substance when it is dissolved that contains ion. So a substance in aqueous solution that contains ions. Right, and so let us type that down and we'll underline the most important points. It is a substance that in aqueous solution would contain ions. Right, very important. So let's have a look at the important parts here. First, going to just change the color to black again. Okay, and so the important points here are a substance that in solution contains ions. Okay, those are the most important parts. I do believe that this would often be a 2 or nothing question. This is a 2-mark question, and often in this they will not allow marks if you don't have all the important parts here. So 9.2, is the pure chromium metal the anode or the cathode of the cell? Give a reason for our answer. But now just a reminder what the electrolytic cell is doing. It's used to electroplate the ring. Now metal will pop off of the one side and they want to have that plate the ring. And so it's not going to happen the other way around. We don't want the ring dissolved plating this this pure chromium metal. We want it the other way around. And so the chromium metal will have to pop off and then attach itself to the ring in a 2-step process. The 2-step process will be the oxidation and reduction. So what happens when this chromium from the chromium metal pops off? It goes from Cr as a metal and it becomes an ion, and the concentrated Cr3 that they have here in aqueous solution. And so the question becomes, how do we go from positive or a neutral ion, chromium, to Cr3 plus? Are we gaining or losing electrons? We are definitely losing 3 electrons in this case. Right. So oxidation is loss, and so oxidation is taking place at the chromium metal, but that is also called the anode, and it is also called the reducing agent. Okay, so you see how we take note of all our information. These 3 things go hand in hand, and please take note of them all together. So is the pure chromium metal the anode or the cathode? Give a reason for your answer. It is the anode, and it is losing electrons. What did we say? We said that the chromium is being oxidized. All right. Our new definition of anodes and cathodes are where the anode is where the oxidation takes place, and cathode is where reduction takes place. And so this should be enough for 2 marks. We've got anode for an answer, and chromium is being oxidized for the reason. 9.3, write down the half reaction that takes place at the ring. See how we're almost there? We've done the half reaction that takes place at the metal. Now we need the reverse to take place. We need this half reaction to occur on the other way around. We need these chromium ions to then each gain electrons to form chromium metal. Right, see how this is a 2-step process. We want on the one side those chromium metal ions to pop off the chromium metal, but on the other side we want them to attach to the ring, and so they need to go back to this metallic form. Right, and so we can write this down just formally. This is in aqueous solution initially, and it gains 3 electrons, and it forms a solid metal on the ring. It is plating the ring. It's creating an outer layer on it that is a chromium layer. Let's have a look here at 9.4. Calculate the total charge transferred when the mass of the pure chromium changes by 2 grams. Oh goodness. Okay, so we're going to do some, what do we call it? Some chemistry here with some stoichiometry, I believe, some calculation, because we might need to know how many of these chromium ions are in 2 grams. Okay, the pure chromium changes by 2 grams. And so how many moles do we have in 1 gram? Because I know for each chromium that pops off, where each 1 mole of chromium that pops off, 3 moles of electrons will pop off. And that's what they're asking us. That's what they're asking us. They're asking us about the total charge transferred. And so for each 3 electrons, 1 chromium. So that's going to be our first port of call, is going to be to figure out how many moles of chromium did we have. And so we have moles of chromium. See how I take note what I'm doing? Moles of Cr. This will be equal to mass over molecular mass. The mass here was 2 grams, and the molecular mass for chromium, I believe, is 52. All right. And so in this case, we have this being equal to 0.038 moles. And they also always tell us at the start of every test that we do, round off your final answer to 2 decimals. This is not our final answer, and so we won't round off to 2 decimals. We will only round off in our final answer. All right, and so the ratio of the number of electrons to chromium is a 3-to-1 ratio. And if I have 0.038 moles of chromium, it would be 3 times as many electrons, and so that calculates to 0.115. And this is the amount of moles of electrons. But how do we know how many electrons we have now? Well, the electron is going to be the number of electrons times Avogadro's constant, the number of moles times Avogadro's constant. And so this is the moles of electrons. And then so now we can say the number of electrons will be equal to 0.115 multiplied by Avogadro's constant, which is 6.2 times 10 to the power of 23. And if you're unsure, this will always be. This is a constant that is given in the formula sheet at the end of the question paper. This gives us a total value of 6.946 times 10 to the power of 22 electrons. Okay, so how much charge is that? How much charge is on one electron? And so the total charge here is going to be the charge on an electron multiplied by the number of electrons. So the total charge is going to be this amount of electrons, 6,946 times 10 to the power of 22, multiplied by the elemental charge. And the elemental charge will be 1,6 times 10 to the power of negative 19. And I cheated a little bit. I did this calculation earlier, but please make sure you're practicing using your calculator. This was 11,113,85 coulomb. That's how much charge. You can also give this in kilocoulomb. It would be 11 kilocoulomb, but I believe this should be fine. Or you can give it in scientific notation as 1,11 times 10 to the power of 4 coulomb. Right. I believe this is giving us just an idea of how to think about and how to look at electrolytic cells. I'd like us to, before we continue onto this next question paper, which will be 2017, I'd like us to just have a brief look at the Science Clinic. The Science Clinic document that I have uploaded for you on Moodle. Please make sure to have a look. I want us to, if you can pause the video, just open up this document and go over to electrochemistry, galvanic cells, or the voltaic cell. It's another name for a galvanic cell. And over here, I'd like to look at the electrolysis of copper chloride, as well as, and I believe it is here, the electrolysis of sodium chloride. Now, the chloralkali industry is not examinable. Specifically, this membrane cell is not examinable. You do not need to know this. But the electrolysis of sodium chloride is still something that we need to be able to do, right? So I'd like us just to pause here on this electrolysis of sodium chloride. I'm going to copy it over for us. All right, moving back to these questions right here. Okay, so I want to just briefly have a look here, just a bit of revision on electrolysis of sodium chloride, which is really just salt water, to be honest. I want us to investigate a little bit. So if you bear with me, have a look here. Brine, that means concentrated salt water. Sodium chloride solution is placed in an electrolytic cell to produce chlorine gas and hydrogen gas and sodium hydroxide solution. That really is the chloralkali industry. But we're not going to look at the industry itself or the membrane cell. I just want to look at the different aspects of this electrolytic cell, because I'm not sure if we will have time going through this next question paper to have a look at this. And so I'd like to discuss it today. On the positive side of this battery, we have the positive side of this battery going over to this and what we call this positive side now being the anode, and the negative side becoming the cathode, because on the anode side we have oxidation taking place. The positive side of the battery is pulling those electrons away from the chlorine, and so the chlorine ion loses that electron and it becomes Cl2 gas, and then it loses those 2 electrons. Those 2 electrons are moving in the direction opposite to conventional current. Just a small reminder, a reminder that conventional current always flows from positive to negative. That's the opposite, the direction that this is conventional current, opposite the direction that electrons move. Electrons always move from the negative side to the positive side. Okay? Do not become confused with those. So just an important one to have a look here. And if on the anode side, we've got these chlorine ions losing their electrons. On the positive side, you've got reduction taking place. On the cathode, we've got reduction taking place. We've got the H2O gaining electrons and becoming hydrogen and, well, hydroxide. Okay. So the net cell can be adding up the left-hand side and the right-hand side with the electrons cancelling out. We had a look at that on our previous session. So please just take note of this. This is the electrolysis of sodium chloride. This is technically part of the chloralkali industry, but however, they can still test you on just the electrolysis of sodium chloride. It is still theory that can be asked. You just don't necessarily need to know about the membrane cell. So going over to this Smart Science Clinic, this membrane cell, this specifically is our chloralkali industry method, okay, which you don't necessarily need to know, but you do need to know standard electrolysis. Okay, I'd like us to continue over onto this next question paper, moving on to 2017. Now we're going to run through this chemistry side again, or the organic chemistry side of it, because I know how comfortable you are with it. But please, if you ever are unsure, pause the video and go over it again. So now let's have a look. Question 2.1. Study the structural formula below. For this compound, write down the homologous series to which it belongs. We see we have carbon-carbon chain split with an oxygen, and then a carbon with a carbonyl, and then the carbon chain continuing. This is very clearly, these are esters. Okay, this is an ester. That's what the homologous series is called. The IUPAC name for this, and a reminder that we always start with what was the alcohol side and then go to the carboxylic acid side. But the naming becomes, in this case, ethyl, and in 2 words, 1, 2, 3, 4 carbons in the other chain, butanoic, not that's butanoic acid is carboxylic acids, but butanoate. Okay, ethyl butanoate. 2.1.1, 0.1.2, 0.1.3. The IUPAC name of the organic acid used in its preparation. Remember, the side with the carbonyl is what was the organic acid, the carboxylic acid. And so it was a 1, 2, 3, 4 carbon chain with, that would be called butanoic acid. All right, a good one there, easy one for 2 marks. 2.1.4. The structural formula of its straight chain unbranched functional isomer. That means the functional isomer, it's got a different functional group. This is important. I believe there will be straight chain. I almost wanted to say that there might be 2 options, but this is straight chain. That means they're unbranched, means there is only one option for us. It means all the carbons, all 6 carbons are in one long chain. And so I will draw the structural formula first by drawing the carbons, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And on the edge, you might already know this because you're quite comfortable, but the functional group isomers of esters are always carboxylic acids. And so right on the edge, we have the OH and the carbonyl group, and then we fill up the rest with hydrogens. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Just a reminder there that each carbon, checking that each carbon has 4 bonds that it is creating, no more and no less. So this is our functional isomer. And for 2 marks, they will have 1 mark allocated to the functional group and 1 mark for the whole formula. Okay, 2.2, write down the structural isomer, or the structural formula of 4-methyl pentan 2-one. All right, this is good. We need to know this is pentan 2-one. We always start with our main branch chain and the functional isomer. And so it's got 1, 2, 3, 4, 5 carbons. And on the second carbon, we've got the 2-one. That means a carbonyl group. That means the double bond to the oxygen. And if we're going to be naming it, it's 1, 2. but because we know on number 4 we have a methyl group, 1, 2, 3, 4, and so here we have a methyl group. I'm going to do it down here, CH with 3 hydrogens attached to it, and now we need to fill up with hydrogens. Please do not miss out, or do not write any substituents, that means like any methyl or ethyl groups like this. This will not be allowed anymore, and so please just watch out, not for structural formula anyway. All right, and so I'm just going to be ensuring that each one of my carbons is 4. This carbon right there needs another hydrogen. That carbon is happy right there. Do not add an extra one there when it's not necessary. Count your hydrogen bonds. 2.3.1. Consider the following structural formula. This is quite a big molecule. Let's have a look. This is an alkyne. This is a branched alkyne. Let's have a look. For this compound, write down the general formula of the homologous series to which it belongs. Study work, CN H2N minus 2. This is beautiful. And we're going to the IUPAC name. Oh, this is very nice one. 2.3.2. Now the IUPAC name. We're going to open this one up, or just enlarge it for us slightly. So the IUPAC name, I'm going to be numbering in green here. The closest carbon on the edge of this chain that would get to my functional group. This is this triple bond over here. I start numbering here, it's 1, 2, 3. If I start numbering from this chain, it's 1, 2, 3. So starting on the right, it honestly doesn't matter. But we get to 3 that side here. It is 1, 2, 3, 4. That doesn't work. 3 is shorter, and so 1, 2, 3, 4. Again, shorter. And so we'd start numbering on the right-hand side. Go 1, 2, 3, 4, 5. If I would go up, it would be 6, 7. So 7 is its longest chain. If I would go straight, it would be 5, 6, 7. That is its longest chain. If I would go down, it would be 6, 7. Right. And so either way, it should be fine. Let's go 5 and 6 and 7. Numbering in this way still allows for our numbering system to be consistent. All right, let's go to the IUPAC name then. Our core of the word is going to be, oh, let's not go green. Let's go, it's going to be hept. But then at the third one, we've got the ine. And so let's just move this up. This is our core of our word. But then we've got substituents here on the 5th carbon and on the 6th carbon. And here we've got an ethyl group, and here we've got a methyl group. And the first ones that we name are always going to be the alphabetical order. And so between ethyl and methyl, we will always mention E first. And so we've got on the 5th carbon, we've got an ethyl group. But then we also have on the 6th carbon a methyl group. And so we've got, oh, I'm missing something. Hold up, I spotted something right here. Look, we've got there another methyl. Got a dimethyl, right? We've got a dimethyl. And so it's not just on 6, it's on 2 and 6. Let's have a look here. Let's erase this. We've got on 2 as well as 6 a dimethyl, hep3-ine. Okay, wonderful. See how important it is to start first on the carbon chain and then label all our substituents, mentioning them in alphabetical order. Not necessarily in order that we find them along the chain, but in alphabetical order. Okay, let's continue on in organic chemistry. This is again still from 2017's paper 2. Now we're moving on to question 3. vapor pressure of substances, of organic substances. And so now we're going to be looking at physical properties of organic substances. That is the topic of this question. The vapor pressure versus temperature graph below was obtained for 4 straight chain, which are unbranched alkanes, P, Q, R, and S. From P to S, each compound differs from the previous compound by a CH group, a CH2 group. So that means that if they're all 4 straight unbranched alkanes, they each differ by a CH2 group. That means that one of the middle carbons are missing on each one, okay, or are being reduced as we go down this line. The vapor pressures are measured in milligrams. What do you call this substance again? The atmospheric pressure is 760 mercury. That's mercury, milligrams, millimeter mercuries. And then we have, give a reason why alkanes are said to be saturated. Well, the definition for saturated compounds are that they have only single bonds. Alkanes are said to be saturated because alkanes contain only single bonds. Now, I believe that there will be a number of other definitions. Some may be saying that they have no double or triple bonds. But I think the most important part here is the word only. Only single bonds, or only or no double or triple bonds. Okay? But please make sure we have that word only has to be there, otherwise it's not a complete reason. 3.2, define vapor pressure. Now the vapor pressure, as we know quite readily from last year or from previous years, is that vapor pressure is, excuse me, is the pressure exerted by vapor in equilibrium with its liquid. Okay, again, this is definition. If you're unsure, please go have a look at the marking guidelines. And here in this case, we have that the vapor pressure is exerted by a vapor in equilibrium with its liquid. This whole section, pressure exerted by a vapor in equilibrium with its liquid, is important. Ooh, I believe there is more to this, in fact, because vapor pressure is in a closed system. Okay, so vapor pressure in a closed system, and I believe that will also be, I have to double check the memo. Let's have a look first. I've got the memo here next to me somewhere. Yeah, in a closed system is important. Okay, just a reminder there. 3.3.1. Use the information on the graph above to answer the questions. What is the effect of an increase in temperature on vapor pressure? Choose from increase, decrease, or no effect. An increase in temperature increases vapor pressure. An increase in vapor pressure will be experienced as more energy is added to this system, this liquid. The vapor pressure, the vapor above it, will experience a higher pressure because there is more energy. The molecules are adding more energy, or are given more energy. Okay, 3.3.2. Which compound has a boiling point of approximately 68 degrees Celsius? Give a reason for your answer. Let's have a look here. 760 atmospheric pressure. Remember, atmospheric pressure, boiling point. Ooh, that's some definition. The boiling point of a substance is where atmospheric pressure is equal to vapor pressure. These are graphs of vapor pressures. And so which graph has a vapor pressure equal to atmospheric pressure at 68 degrees? Let's have a look. 68 degrees is here somewhere. And so that is going to be where vapor pressure is equal to atmospheric pressure. Atmospheric pressure is here at 760. And so I believe it will be substance Q. And the reason, fully explain the answer. no, hold on. Give a reason for the answer. Here we're going to say something along the lines of boiling point is where vapor pressure is equal to atmospheric pressure. That's simply definition of boiling point. And we see this, I think that should be enough. This is a 2-mark question. I believe that should be enough. It is the temperature where this graph is equal to the vapor pressure. Yeah, so it is the substance, the compound whose graph crosses the atmospheric pressure at that temperature. Okay, this is a very complete answer. We're fully explaining it. I just don't want to make, I'm not sure exactly what they're after, but I think this fully explains. So we are not going to be missing out on any marks. We give the definition, that's important. The definition of boiling point, that's how we make this decision. We need to know what the boiling point's definition is, but then how we interpret this in our second sentence and linking the two concepts. Okay, let's have a look. 3.3.3, which compound has the longest chain length? Now, remember a reminder in how chain length affects boiling point and vapor pressure. It is that we have the strongest intermolecular forces causing a higher boiling point. But how does the chain length affect that? Now, at a, we see that this is going to be, let's have a look. Our boiling point for substance P is here at 37. But at Q, that was 68. For R, it was just under 100. And for S, I believe S will be on here. It will be have the highest boiling point, and then for that reason, it will have the highest intermolecular forces. Okay, and we know that chain length is directly proportional to the intermolecular forces, and so we will say that which compound has the longest chain length. We'll say that S has the longest chain length. Okay. And so at any given temperature, we can see that at any temperature that it has the lowest vapor pressure, or it has the highest boiling point. Highest boiling point. But because this is a vapor pressure question, we're talking about lowest vapor pressure. We used vapor pressure to determine or to talk about highest boiling point. And so let's talk about the lowest vapor pressure, because this is a question on lowest vapor pressure. Okay, and now we know that this is got the strongest intermolecular forces. Intermolecular forces, just going to shorten that for us. And then the highest energy needed. Therefore, longest chain length. All right. Okay, and that should be, this is a 4-mark question. Let's have a look. It's going to be 1 for the statement, and then 1 for 1, 2, 3. And then usually they don't allow us the final answer because that is the question. All right. So a good one for 4 marks. Let's have a look then as we continue. 3.4, compound P has 5 carbon atoms. Compound P has 5 carbon atoms. Also, just before we continue, I'd like to just point out that they said from P to S, each compound differs from the previous compound by a CH2 group. Important. Each compound differs from the previous with a CH2 group. So if they tell us about what P is, And as P goes to S, the chains become longer. We can know now exactly what each of these molecules are, each of these compounds are. Okay, so 3.4.1, draw the structural formula of a chain isomer of P. All right, let's have a look. We've got 5 carbon atoms. Let's first draw ourselves, what 3.4, what P would look like. And so let's do that here on the side. We're going to, in yellow, just draw what P would be. It was an unbranched alkane. So 1, 2, 3, 4, 5. And so how do we draw a structural formula of a chain isomer? It's not a structural isomer, it's a chain isomer. So it will still be only an alkane. Now there are multiple ways that we can do this. We can make it a butane with somewhere another carbon, or we could possibly make it a propane. I really love the propane on this, because the propane is quite symmetrical to me, to my eyes. And we've got a hydrogen on each one. Okay, so you can often play around just by making quick sketches. In this case, you can do either of these. I'm going to use the propane, as I mentioned. This propane with the 2 ethyl groups, so the 2 methyl groups, is quite satisfying. Right, so we draw the structural formula, and so we've got 3 carbons for our main chain, and then on the central carbon we've got the 2 methyl groups, and with its hydrogens on each side. If we're going to be drawing this propane, it is going to be important just for us to recognize we might need to draw a little smaller than we're comfortable with, or we draw our main carbon chain quite large. Let's have a look then at 3.4.2. Let's continue down this line of questions. 3.4.2. How will the vapor pressure of this isomer compare with that of compound P? And here we need to talk about branching and how branching affects it. And so vapor pressure, branching reduces the surface area. And so by reducing the surface area, we are decreasing intermolecular forces. And when we decrease intermolecular forces, the vapor pressure becomes higher. Or by decreasing intermolecular forces, boiling point becomes lower. It boils easier. But boiling point and low vapor pressure are inversely proportional. Look at this question we did earlier. Highest boiling point happens at lowest vapor pressure. These 2 concepts are inversely proportional. And so how will the vapor pressure of this isomer, compare with that of compound P? It is more branched, weaker intermolecular forces. It will have a higher vapor pressure. And so they say choose from higher than, lower than, or equal to. I will say higher than, exactly as one of the options that they give me. Okay, higher than. Okay, we've got about 5 minutes left. I believe we can continue on to this question 4. Now we are on organic chemistry, but reactions on organic chemistry. And yes, we might need another reminder. This is a lot of information on reactions of organic chemistry. And so I brought this notepad, this page over for us again today. Now let's have a look. The flow diagram below shows an alcohol, compound P. Here we've got an alcohol, can be used to prepare other organic compounds. Now we know alcohols can be made by elimination reactions, but they can also be made, or they can also be used to create haloalkanes with substitutions, or they can be made with haloalkanes to alcohols and hydrolysis, okay, or with addition. We have hydration taking place with the addition reactions, and so multiple things can be made there that can be used to prepare other organic compounds. The letters A to E represent different organic reactions. Okay, so A, B, C, D, and E all refer to specific type of reactions. The letters with organic reactions with X, Y, and Z being the compounds. X, Y, and Z being compounds. Let's have a look here. 4.1. Is compound P primary, secondary, or tertiary? In this case, we have a look where the functional group lies. The functional group is attached to a carbon that is attached to how many other carbons? And so in this case, it's going to be 2. Our answer is secondary. And the reason is going to be that the carbon to which the OH is bonded, the carbon to which OH is bonded to two other carbons. Okay. Important there, that's just that explanation. It is the carbon to which the functional group is bonded to two other carbons. Let's have a look. We continue here. 4.2.1. Write down the type of elimination reaction that is represented by A. Okay, so we're going from something that is an alcohol to an alkene. Okay, so it's not substitution because it is going to an alkene. Going from an alcohol, it is an elimination. That's right, it is elimination, and so this will be dehydration. If hydration is the adding of water to make an alcohol, then dehydration would be the removing of water to make an alkene. Dehydration. I got hydration on the mind. So the answer is dehydration. And in this case, they are asking for a very specific type of elimination, so we have to give the very specific type of elimination. We cannot just say elimination as we have been able to do in many old exam papers. We see they often just allow for elimination, but in this, it's not the case. 4.2.2, the addition reaction represented by B. And so the addition reaction represented by B, going from an alkene to water, I've just mentioned it, is the opposite of dehydration. It is hydration. All right, going on to the next question, 4.2.3. The elimination reaction represented by D. We're going from this organic compound, which we got from adding hydrogen bromide. Oh, this is some form of bromo. This is some form of bromo. We've replaced the OH with a hydrogen and a bromide. Okay, let's have a look. This must mean this is a haloalkane, going from an haloalkane to an alkene. This is going to be subtracting one bromine and one hydrogen. That's dehydrohalogenation. So we're moving a hydrogen, a dehydro, and a halogen, halogenation. Dehydrohalogenation. 4.3. 4.3 here says sodium hydroxide, and let's finish 4.3 and then we can continue on next time. 4.3, sodium hydroxide is used as one of the reactants in reaction C. Let's have a look there. You've got reaction C going from that halogen or that haloalkane back to compound P. Okay, again, that is some substitution. We're going from haloalkane to an alcohol. That's called hydrolysis. And so when we have the question being sodium hydroxide is used as one of the reactants in reaction C, what type of reaction takes place here? That is hydrolysis. Okay, 4.3.2, state the two reaction conditions for this reaction. And again, we might need to just remind ourselves, reaction conditions for hydrolysis, we're going from what do we call here? We've got dilute sodium hydroxide. I believe, let's have a look at that. Sodium hydroxide, beautiful. Reaction conditions are going to be a lot of heat and some sodium hydroxide. So we've got dilute sodium hydroxide and a lot of heat. All right, let's go into 4.3.3 and then the last one for this evening, 4.3.3, write down the IUPAC name of compound X. And so compound X has the substance, this functional group being replaced, immediately substituted. Is not going to the alkene and then to the compound X. It is being immediately replaced with our bromine, okay, with our hydrogen bromide. And so let's have a look here. We've got, it is still a 1, 2, 3, 4 carbon chain, but with on the second carbon a bromine. And so we have that 2 bromo, but it is still a butane. Right. Okay, actually, we still got time. Let's finish this one. We're so close to the end of this question. 4.4, write down the formula of the inorganic reactant needed for reaction D. That is going from the haloalkane to an alkene. Again, that is elimination. Okay, but going back to our notes, we've got elimination reaction going from an haloalkane to alkene. Question asks, using write down the formula of the inorganic reactant. Now, what is the inorganic reactant that is needed for haloalkane to alkenes? Is it concentrated strong base in ethanol plus heat? And in this case, we want a strong base. That is sodium hydroxide is a very common one for us that we know of, a very strong base. 4.5, using structural formula, write down a balanced equation for reaction E. Are we going to an alkene that is 4 carbons that is taking place with hydrogen and platinum? Now that feels like addition for me, ladies and gentlemen. So let's have a look here. 4.5. 4.5 is going to be, I feel like, addition. Structural formula, write down balanced chemical reaction equation for reaction E. So let's have a look here. We have got that butene, I believe, with the butene being where? Where's the double bond? And so now we might need to go back to the Zaitsev and Markovnikov's rules. Now, remember when this OH is being taken away in reaction A, the hydrogen that is taken is not from one of the H's, because they each have 3 hydrogens, but from a carbon that only has 2 hydrogens. We take from the poor and give to the rich, right? Okay, but that means that those H's and O's will be taken, and so that leaves the double bond right there in the middle. We've got now the hydrogen there and the hydrogen there, filling up the empty spaces, and the hydrogen there, and let's make it nice and symmetrical. Okay, beautiful. So we've got this butene, and it is reacting with my 2 hydrogens, and it is creating a product. And the product that is created is going to be the same alkane, just without the double bonds. All right. Structural formula is given with all bonds being shown. Please do not forget that. Don't take any shortcuts. All right. And so in this case, are they asking for us? I would still tell, even though they did give it, I would tell us that there was some catalyst here. That was the platinum catalyst. Let's go into this very last question, 4.6. Write down the IUPAC name of compound Z, and this is butane. All right. I'd say let's stop there today, and we'll have a look continuing on chemistry in our next session. I really do hope that you can make use of this, and that you are going to be working with me on this new question paper from 2017. All right. Mikle, I hope you have a wonderful evening. Good luck, and I'll see you again next week. Bye-bye.